We discuss the topic conservation of principle of conservation of energy. Principle of conservation of energy. The topic is principle of conservation of energy. When we throw a ball, then the chemical energy stored in our body gets transformed as the kinetic energy of the ball. When we throw a ball in upward direction, then chemical energy stored in our body gets transformed to the kinetic energy of the ball. And as the ball moves up, as the ball moves, the kinetic energy continuously decreases. As the ball moves up, the kinetic energy decreases. And at the highest point, when the ball reaches the highest point, the total kinetic energy gets transformed into the potential energy of the ball. And when the ball moves in downward direction, when the ball comes in downward direction after attaining the maximum height, then again potential energy goes on decreasing. And potential, when the ball strikes the ground, the potential, the potential energy is converted into sound energy and light energy. So at every point of the motion, there is a change in kinetic energy, there is change in energy. At every point of motion, there is a change in energy. When kinetic energy decreases, potential energy increases. When potential energy decreases, kinetic energy increases. But the total energy remains conserved at every point. So this is about conservation of energy. When a ball is thrown up, the chemical energy stored in our body gets transformed as the kinetic energy of the ball, and as the ball moves up, the kinetic energy gradually decreases, and when the ball reaches the highest point, total kinetic energy gets transformed into the potential energy of the ball, and when the ball moves downward direction, its potential energy goes on decreasing, and when it strikes the ground, the ball or the object, when it strikes the ground, its energy gets transformed into light energy and sound energy. So we can say that energy can neither be created nor be destroyed. Energy can neither be created energy can neither be created nor be destroyed. Energy can neither be created nor be destroyed. It may be transformed from one form to another. It may be transformed from one form to another. From one form to another. but the total energy remains conserved. But the total energy of the body always remains constant. But the total energy of the body, but the total energy of the body always remains constant. This is the principle of conservation of energy. Now we discuss the next topic, that is power. Power is defined as the rate of doing work. Power is defined as the rate of doing work. Power is defined as the rate of doing work, and average power is given by P average equals to work done upon time. Average power is given by work done upon time. It is a scalar quantity. It is a scalar quantity. Power is a scalar quantity because it is the ratio of two scalar quantity. Why it is a scalar quantity? Because it is the ratio of two scalar quantities. And the ratio of two scalar quantity always gives the scalar quantity. So power is a scalar quantity and average power is defined as ratio of work and time. And it is a scalar quantity because it is the ratio of two scalar quantity. Work done is a scalar quantity and time is also a scalar quantity. Now the dimensions of power. So power equals to work done upon time, and work done equals to force into displacement. Work done equals to force into displacement and upon time. Then force equals to mass into acceleration. mL t raised to the power minus 2. Force equals to mass into acceleration, and displacement is represented by L and time is represented by T. So we get mL square and t raised to the power minus 2 and t raised to the power minus 1. T raised to the power minus 3. So the dimensions of power is mL square and t raised to the power minus 3. SI unit of power. SI unit of power is watt. SI unit of power is watt, and 1 watt is equals to 1 joule upon 1 second. 1 watt equals to joule per second, and bigger unit of power is kilowatt. Bigger unit of power. Bigger unit of power is kilowatt. Short way written as kW. And horsepower. In short form, it is represented by HP. So the bigger unit of power is kilowatt and HP. And 1 kilowatt equals to 10 raised to the power 3 watt. 1 kilowatt equals to 1000 watt. And 1 horsepower is given by equals to 746 watt. 1 kilowatt equals to 10 raised to the power 3 watt. 1 horsepower equals to 746 watt. So this is about the basic concept of power. Power is defined as the rate of doing work, and average power P average is given by W upon T, work done upon time. And power is a scalar quantity because power is the ratio of two scalar quantity, work done and time. Work done is a scalar quantity and time is also a scalar quantity. So the ratio of two scalar quantities always gives a scalar quantity. And the dimensions of power is ml square t raised to the power minus 3. SI unit of power is watt, and 1 watt equals to 1 joule upon 1 second, and bigger unit of power is kilowatt, and horsepower 1 kilowatt equals to 10 raised to the power 3 watt, and 1 horsepower is equals to 746 watt. Now we talk about the instantaneous power. Instantaneous power. If work delta W is performed in a very short time interval, if delta W work, if delta W work performed in a very short interval time, if delta W work performed in a very short interval of time, if delta W work is performed in a very short interval of time, delta T, then instantaneous power is given by, if delta W is also the small work, so if a small work delta W is performed in a small time delta T, then instantaneous power is given by P instantaneous equals to limit delta T tends to 0, delta W by delta T. Instantaneous power is given by limit P instantaneous equals to limit delta T tends to 0, delta W by delta T, where delta W is the small amount of work done and delta T is the small time. And limit delta T tends to 0, delta W by delta T is given by dW by dt. So dW by dt is called instantaneous, or limit delta T tends to 0, delta W by delta T. When we take the limit for a small quantity, ratio of a small quantity, then we get the instantaneous value of power dW by dt. Now we know work done. dW, the small amount of work done, is given by F dot ds. The small amount of work done dW is given by F dot ds. So put the value of dW. So from first, instantaneous power P instantaneous equals to dW by dt, and at the place of dW we can write F dot ds upon dt, and this also can be written as F dot ds by dt, and ds by dt, ds is the small distance, so rate of change of distance or displacement equals to velocity. So ds by dt is given by v. So instantaneous power is equals to F dot v. Instantaneous power is given by F dot v, and it is the dot product. It is the dot product. So it is given by P instantaneous equals to Fv cos theta, where theta is the angle between F and V. P instantaneous equals to Fv cos theta, where theta is the angle between F and V. So this was about the instantaneous power. Is if delta W work is performed, in a very small interval of time delta t, then instantaneous power P instantaneous is given by limit delta t tends to 0, delta W by delta t. Delta W by delta t, a small work done upon a small time. And when we put the limit delta t tends to 0 in a small work done upon a small time, then it becomes instantaneous, which is written as dW by dt. Then we know that force, small work done, dW is defined as force into displacement, dot product of force vector and displacement vector. So dW equals to F dot ds, and we put the value of dW in first equation. So P instantaneous equals to F dot ds at the place of dW, F dot ds upon dt, and we can separate ds by dt. So F dot ds by dt, and ds by dt is given by velocity. So instantaneous power is given by F dot v, and F dot v is written as Fv cos theta. So instantaneous power is equals to Fv cos theta. Now the next topic is kilowatt hour. Kilowatt hour. kWh. Kilowatt hour, which is in short form written as kWh. So kWh or kilowatt hour is a commercial unit of energy. Kilowatt hour kilowatt hour and BOT, Board of Trade, kilowatt hour or Board of Trade, BOT, is the commercial unit of electrical energy. Commercial unit of electrical energy. Kilowatt hour, which is also written as Board of Trade, Board of Trade, BOT, is the commercial unit of electrical energy, and 1 kilowatt hour is the electrical energy consumed. 1 kilowatt hour is the electrical energy One kilowatt hour is the electrical energy consumed. 1 kWh, 1 kilowatt hour is the electrical energy consumed by an electrical appliance. Consumed by an electrical appliance of 1000 watt in 1 hour. In 1 hour. 1 kilowatt hour is the 1 kilowatt hour is the electrical energy consumed by an electrical appliance. By an electrical appliance of 1000 watt in 1 hour. Means 1 kilowatt hour is equals to 1 kilowatt into 1 hour. 1 kilowatt is also equals to 1000 watt. So 1 kilowatt hour is equals to 1 kilowatt into 1 hour, and 1 kilowatt is given by 1000 watt into 1 hour. 1 hour is given as 3600 and second. In 1 hour there is 60 into 60 seconds. And watt is given as joule per second. So 1000 watt is written as joule upon second into 3600 second. Second and second gets cancelled and we get the result 3.6 into 10 raised to the power 6 joule. So 1 kilowatt hour 1 kWh, 1 kilowatt hour, is equals to 3.6 into 10 raised to the power 6 joule. So kilowatt hour or board of trade unit kilowatt hour or board of trade unit is the commercial unit of electrical energy, and 1 kilowatt hour is the electrical energy consumed by an electrical appliance of 1000 watt in 1 hour. Now we see one numericals based on power. The question is, a car of mass 2000 kg is lifted up a distance of 30 meters. The mass of car is given by 2000 kg. A car of mass 2000 kg. A car of mass 2000 kg is lifted up a distance of 30 meters by a crane in 1 minute. It is lifted by a distance of 30 meters. A car of mass 2000 kg is lifted up a distance of 30 meters in time 1 minute. So time is given 1 minute, means 60 seconds. In 60 seconds, a car of mass 2000 kg is lifted up a distance of 30 meters. A second crane does the same job in 2 minutes. The first crane do the job in 60 seconds, and there is a second crane who lift the car. The second crane lift the car in 2 minutes, means time T2 is given. Time T2 is 2 minutes. 2 minutes means 120 seconds. So in our question it is given that there is a car of mass 2000 kg which is lifted up by a crane 30-meter height in time 60 seconds, and another crane lifted the same car in 2 minutes, means in 120 seconds. So do the cranes consume the same or different amounts of fuel? Do the cranes consume same or different amount of fuel? Do the cranes consume same or different amount of fuel? And what is the power supplied by each crane? What is the power supplied by each crane? What is the power supplied by each crane? So we have to calculate the power supplied by each crane and work done by each crane. You know, work done equals to force into displacement. So work done by each crane. Work done by each crane, and W equals to F into S. W equals to force into displacement, and force is given by mg. Force is mg and height is in terms of h. We have given a height h equals to 30 meter. So work done by each crane. So mass is 2000 and G is 9.8. G is 9.8 and height is 30 meter. By both the cranes, the same work has to be done because mass is same, G is constant and height is same. And the value we get 5.88 into 10 raised to the power 5 joule. 5.88 into 10 raised to the power 5 joule. So this is the work done by each of the crane. Now we have to calculate the power. So power supplied by first crane P1. Power supplied by first crane. Power supplied by first crane. So power equals to work done upon time. Work done is 5.88 into 10 to the power 5 and time is 60 seconds. So this is the power supplied by the first crane, which is 9800 watt. 9800 watt. Now we calculate the power P2, means power supplied by second crane. Power supplied by second crane. The same formula will be used. Work done upon time P2, 5.88 into 10 raised to the power 5 upon 120, which is 4900 watt. So the first power supplied by first crane is 9800 watt and by second crane is 4900 watt, and as both the cranes do same amount of work, as both the crane do the same amount of work, so they consume the same fuel. They consume the same fuel. They consume the equal amount of fuel. Equal amount of fuel. Because they perform the same amount of work. They perform the same amount of work. Therefore, they consume the equal amount of fuel.